Hello and welcome to my online presentation for Chapter 30. Here we're going to be discussing electromagnetic waves and theory behind electromagnetic. The goal here is to establish a set of equations that can define electromagnetic waves, describe them, allow us to work with them in a scientific way. So the tools that we need here are the Maxwell Equations, which really is a set of 4 equations that describes everything that we've done in class so far. So that's kind of exciting, where now we're going to put this stuff to practice here. We need to talk about what a transverse wave is, a sinusoidal wave that travels perpendicular to the sinusoids. So we're going to see what that looks like. And we need to discuss how much energy is stored in these waves. And it turns out that energy is stored in a magnetic and in an electric field. So we're going to need to know that theory. An electromagnetic wave can be, an example would be visible light, UV, radio waves, television waves, the list goes on. So the Maxwell equations are really a combined set of equations for everything that we've done so far. So Gauss's law for electric fields, we've seen in early chapters, that deals with enclosed charge and electric flux. Gauss's law for magnetism, we've seen recently, that deals with the fact that there are no magnetic monopoles. So every magnetic field line leaving the north pole of a magnet eventually reaches the south pole of that magnet. And so if you have a closed surface, the same amount of flux is going to enter the surface as what left. So we're left with a net flux of 0 on that closed surface. Faraday's law for induction, normally we're used to seeing EMF equal to negative d phi b dt. Now we're seeing something slightly different here, so we're going to talk about that later and how we came up with this. And then Ampere's law, we need to modify. So the first term on the right-hand side, mu sub 0 I enclosed, you've seen that before. You have not seen the second portion of the right-hand side, and we're going to talk about where that comes from. So remember, Ampere's law is describing current flowing through a surface and a line integral around that surface. So we draw a path around the surface through which current is flowing, and then if we integrate, the integral of b dot dl equals mu sub 0 I enclosed by the surface. But this is basically equating magnetic field around a path with current flow, but we can also get magnetic fields surrounding a path when no current is actually flowing, but just when electric field is changing in that region. So we need to account for that. That's where the discrepancy comes in. We need to account for changing electric fields and what they do to magnetic field. And so here's how we're going to do it. So we draw a picture of these capacitor plates, and we see that we can draw a surface so that the path for Ampere's law bounds or encloses 2 different surfaces. One is a dome surface that extends in through the back of the left-hand plate or into the electric field area, right? But does not have current passing through it. So you see automatically that no current passes through that dome-like surface. And then also the path bounds or encloses the front side or the left side surface, which is like a disc, and through that surface current does flow. That current's listed as IC, or conventional current, which is basically the flow of charge onto this capacitor plate, and that would give you IC. So if we use a parallel plate capacitor to derive this Ampere's law, current will definitely be flowing as charge collects on the plates. So we have I conventional that we can calculate. But also, as the electric field changes, we can represent that as a virtual current or a displacement current. So let's see how that works. So current is defined as dq dt, but remember for a capacitor, Q is equal to CV, so dCV dt is the same thing. And then if we remember for a parallel plate capacitor, C is epsilon sub 0 A over D, and V is ED. So plugging those in, we still have the same value. So now if we simplify and then remove terms out of the derivative that are constants, we get epsilon sub 0 A dE dt. Now what is A times dE dt? It's area times electric field change, which is d flux dt. And so we're left with displacement current or virtual current equal to epsilon sub 0 d phi e dt. And what this is showing is if you have a changing electric field through a surface, you can define it or explain it as in terms of a displacement current. And so then we can plug it into Ampere's law. So Ampere's law now is mu sub 0 IC enclosed plus mu sub 0 ID enclosed. So this accounts for displacement currents and for conventional currents. And so in other words, it accounts for real currents and for changing electric fields. And it's saying that either of those two things will generate a magnetic field. Currents generate magnetic fields. Changing electric fields generate magnetic fields. Interesting. So now let's look at how we came up with a modified version of Faraday's law. So the original Faraday's law says that EMF is equal to changing magnetic flux. Delta V then is equal to changing magnetic flux. But if we look at the second equation here, remember delta V is E dot dl, which is this came from the work is equal to force times distance equation, as I mentioned in chapter 23. But we also note that since electric fields in our example problems that we did back then were conservative, the EMF around the closed path would equal 0, because the work around the closed path would equal 0, net work. But in the case of magnetic induction, this is not a conservative electric force. And so we can conclude that yes, we can have an EMF around a closed path. So the integral of E dot dl on a closed path now is equal to changing magnetic flux with respect to time. And so what we've done is we've shown here that a changing magnetic field gives us an electric field. And previously in the modified Ampere's law, we found that a changing electric field gives us a magnetic field. Now, how much energy is stored by these fields? Well, we've seen already the left-hand side equations showing energy stored by an inductor and a capacitor. Well, that energy is stored inside the field itself, and we can define an energy density for that field. And that energy density is 1/2 epsilon sub 0 E squared. So now what I'd like each student to do is to take time to derive these for yourself. And the way that you do it is by saying capacitance is equal to epsilon sub 0 A over D for a capacitor, a parallel plate capacitor. So if we were to plug in epsilon sub 0 A over D, and then potential is ED, you can see that these are going to simplify to give you 1/2 epsilon sub 0 E squared times area times distance between the plates. But that area times distance between the plates will give you volume. So Something similar can be done with an inductor. I actually talked about this last class, so please review the notes. So now what we're left with is energy density equations for each type of field. So how much energy is stored in an electric field in a region of space, and how much energy is stored in a magnetic field in a region of space. Multiplying each of these by the volume of space occupied will give you total energy storage. So now what we've seen is Faraday's law says that a changing magnetic field gives us an electric field. Ampere's law says a changing electric field gives us a magnetic field. So if we can picture a television or radio antenna that is sending current up and down and changing direction, we end up having a changing electric field, a changing magnetic field. And so these two fields kind of build on each other and end up traveling outward through space. And we're going to see how that works. So here's a picture of an antenna, maybe like a radio tower antenna. And we've kind of drawn it with a dip in the antenna to the left, as shown. And the reason for this is so that you can see the shape that the fields would take. So if we have current flowing upward, you can see that the electric field lines take circular shapes, clockwise circular shapes, as shown. And the reason for that is that a positive charge would try and move around across this gap, and so we're going to get electric field lines around the gap. And then also, if we put our thumb in the direction of this current, we can see that magnetic field lines go into the page on the right-hand side, out of the page on the left-hand side. So this is the snapshot as current is flowing upward, what the electric and magnetic fields look like. Now this is energy in space that's already been placed there, so that energy is not going anywhere. If we were to look, if we suddenly shut current off, this energy is still going to be present, and it's just going to travel outward. So these fields extend indefinitely, but they get weaker as the further away we get from the antenna. Now, if at some time later current changes direction, such as the case with an oscillating current, we can see that the electric field and the magnetic fields now take opposite directions as well. But the original energy now has traveled outward a bit and is still present. And so the original field lines fold around to meet the second set, the new set of field lines. And what we're left with is a wave of energy that's traveling outward from this antenna. So hopefully you can envision this. If you can't, you could find graphics online that would show you this. But this one does a pretty good job of showing what that energy looks like. So this is called near-field radiation for the antenna. Now you can picture these bubbles of energy. As they continue to move away from the tower, they're going to become straighter and straighter until eventually we're left with an electric field and a magnetic field that are traveling as a wave through space. And so that's what this is showing. So the direction of travel, the fact that these waves straighten out. So on the right-hand side, this is far field radiation, or far away from the antenna, what the energy looks like. And what it looks like is a electric field pointing up and down vertically, and a magnetic field coming into or out of the page, as shown. So they're at 90-degree angles to each other, and they're at 90-degree angles to the direction of travel. So that's known as a transverse wave. This is a electromagnetic transverse wave, where you have magnetic fields and electric fields in phase with each other, meaning their peaks line up with each other, their troughs line up with each other, but they are oscillated at 90 degrees to each other. Okay, so here what we're going to do is we're showing for a particular example some of this wave math. So here the wavelength is equal to 15 meters in my example. And what I'm doing is I'm taking a snapshot at time equal to 0 of this wave. So even though the wave is eventually going to travel, right now it's stationary in time because we took a snapshot of it. Now, if we were to plug in different points for x here, which is the variable shown in this case, if we plug in, say, x equal to lambda, so that's the point all the way to the right-hand side at the peak of the wave, then we're going to get amplitude times cosine of 2 pi lambda over lambda, which is cosine of 2 pi, so that gives us 1, and y of x and 0, if x is equal to lambda, is going to give us amplitude, a. And that's correct for this picture. If we plug in x equal to 0, so that's all the way to the left side where we're also at a maximum peak, we're going to get cosine 0, which is gives us a value of 1 times amplitude. And so there we're saying that y is at maximum, or y is equal to a. And so that point is correct. If we look at the middle of the wave, so that would be lambda halves, x equal to lambda halves, y of lambda halves and 0 gives us a cosine 2 pi over 2, because the two lambdas cancel each other. And so we're left with cosine pi, which will give us negative a, or maximum negative value. And so that works as well. So I mean, every single point here will work with this equation. So the equation seems to be correct, representing the wave along the x-axis, snapshotted in time. So now what we're going to do is we're going to define something called wave number. And so wave number k is 2 pi over lambda. So it's just a variable to make things more simple. And so as shown, now y as a function of x and time at time 0 is a cosine kx. And so for instance, amplitude here is 1. K is 2 pi over lambda. If you were to plug that in, you get 0.418. And so I'm just showing for this particular example what we would get. So now what we need to do, so we have basically the part of equation dealing with the wave in space. Now we have to add the time variable in. So one thing we know is that in time t, the wave would have traveled the distance of speed times t. So that term's going to come into play here. So now what happens is if we want to describe the wave the way we used to, we need to subtract off how it moved. So that's essentially what we're doing here, is we're saying we had the equation y of x and 0 equal to a cosine x over lambda times 2 pi. Now we need to subtract off the change to kind of bring the wave where it used to be and to represent it properly. So x minus speed times time over lambda is what we end up with. But speed is equal to wavelength times frequency, because wavelength is measured in meters, and frequency is measured in cycles per second. So we're left with meters per second here. So speed is lambda f, or frequency is speed over lambda. And so we can see we have a speed over lambda term up top that we're going to replace with frequency. And so we're left with this equation, x over lambda minus frequency times time. But remember, omega is equal to 2 pi f, and here we're left with a 2 pi f, and so we can see that we're going to replace this with an omega t, and we do. So we're left with 2 pi x over lambda minus omega t. But remember, k is 2 pi over lambda. And so here is the equation that we're looking for. So this is describing what the amplitude is of a transverse wave traveling through space with speed nu, speed equal to lambda times frequency, and wave number equal to k, which is 2 pi over the wavelength. So this is what we're going to use. If this doesn't make sense, be sure to review wave representation for transverse waves. This will be in your book, and also there's several resources online. Okay, so the assumptions that we're going to use from here forward are that we have plane waves, meaning we're far from the antenna. The electric and magnetic fields are traveling in a single direction. They're not curved. And we're operating in a vacuum, and that the wave is traveling in the x direction, so that speed is equal to speed times I hat. Excuse me, velocity is equal to speed times I hat. We're going to assume that the electric field is parallel to the y-axis, magnetic field is parallel to the z-axis. So let's get started. So in an empty vacuum, there is no enclosed charge, there's no flowing current, and so both of those are 0. So now here's what the Maxwell equations give us. 2 kind of boring equations up top, which we're not going to end up using after all, and then 2 equations that deal with changing magnetic field and changing electric field. We are going to use those. So we're going to use the 2 bottom Maxwell equations. We're going to use the transverse wave equation, and we're going to use the energy density equations. And that's how we'll build our theory. Now we have everything we need to develop the electromagnetic wave theory. So this is very algebra intense in these upcoming slides, so please be sure to rewatch this if need be. If the wave has wavelength lambda and frequency f, then we plug in to get the following. And these should make sense based on the wave equations and our definitions for the wave number and for omega. Okay, so now this picture that we're showing here is our assumed electric field direction and magnetic field direction. So first thing we need to find out is, did we draw this correctly? Because the electric field is pointing straight up on the right-hand side of this wave, and if that's pointing up, then would the magnetic field be pointing into the page or out of the page? So that's what we're asking. And the answer is that because the wave is moving to the right, you can see that magnetic fields will be decreasing at some point in the future here. Like, so if we step time forward, the magnetic field is going to decrease through the path that we have drawn. So that means that induced magnetic fields must increase out of the page. And if we put our thumb in the direction of electric field, which would be like the current direction, we see that magnetic flux through this area that we've drawn, through the path that we've drawn, will be increasing out of the page to compensate, and that's what we want. So hopefully that makes sense. And so the direction of travel is to the right, and that means that E cross B will give us the direction of the wave's travel. So if we put our fingers in the direction of E, wave them toward B, our thumb gives us the direction of travel, which is to the right. So now what we have is two pictures. The one that I just showed on the last slide, that's going to be used to apply Faraday's law using E dot dl. So we've drawn a path, an integration path with electric field on that path. And that E dot dl is going to be equal to the changing flux through that area bounded by the curve. So and then the bottom picture is to apply Ampere's law. So here we've drawn integration path around which we have magnetic field lines, and that will have electric flux passing through it. So these are kind of the pictures that we're going to be using for the entire derivation. Okay, so for the top picture, we're applying E dot dl equal to changing magnetic flux. And so we're going to do this, first we're going to analyze the left-hand side, and then we're going to analyze the right-hand side. So for the left-hand side, E dot dl, well, automatically we see that on the top and bottom of our integration path, electric field makes a 90-degree angle with the path. So E dot dl is 0. So the top and bottom do not contribute anything. So the sides are the only contributing lengths. And so each side has length delta y, as shown. And what we're going to say is that we have electric field E on the left-hand side, and then on the right-hand side we have that same value E plus some small value in addition to it because it's taller. And we're going to call that small value dE, or just very small change in electric field. So here in this snapshot we see that the left-hand side becomes E plus dE delta y minus E delta y. And so that simplifies to dE delta y. So this is just by simply applying E dot dl to the integration path shown. Now we look at the right-hand side. So we're looking at dt of magnetic flux, which would be equal to the area times dB dt. So the area is delta y, height, and dx, width. So dx is just a small change in the x direction. So delta y dx gives us the area, dB dt gives us the magnetic field change through that area. So the multiplication of the two gives us d phi dt. So now, since we have the left-hand side and the right-hand side, we need to equate them. And when we do equate them, that gives us this equation. And notice that the delta y's will cancel. And so now what we're going to do is divide through by dx, and we'll get an equation that we can use. So this is an equation that we're going to set aside and use. And now we're going to take a look at the second picture, in which we're going to apply Ampere's law. So we've applied Faraday's law, now we're going to apply Ampere's law to this one. Okay, so, and keep in mind the reason we're doing this is to develop an equation that represents the wave. There's a deeper reason why we're doing this, and that is to develop an equation that shows the speed of that wave. And as it turns out, that speed is the speed of light. So we're going to see that. So applying B dot dl, we're going to do the same thing. Take the left-hand side first. And so the left-hand side equation gives us B dot dl, and we did it pretty much the same way we did Faraday's law. So that would be B times delta Z minus B plus dB delta Z. So it's basically saying that the top and bottom portions don't contribute because the magnetic field makes a 90-degree angle with the path. So the only thing that contributes is the sides. And since the magnetic field goes against the integration path on the right-hand side, that's going to be the subtracted side. And so this simplifies to negative dB delta Z. The right-hand side of the equation, again, we're treating it the same way we did the last portion, which is area dx times delta Z now, times electric field passing through that area. Rate change of electric field passing through that area gives us d phi dt. And the mu sub 0 epsilon sub 0 come along for the ride. So now, equating the left-hand side and the right-hand side gives us this equation. And we see again that the delta z's will cancel, giving us this equation. And now all we have to do is divide through by dx to get our final usable equation here. And so now we have this equation plus the one we derived from Faraday's law. So what are we going to do with these? So taking the two pictures and applying Faraday's law and Ampere's law gives us these two equations. And so we're going to actually apply those equations to our transverse wave for the electric and magnetic fields. Now to do this, we have to use something called partial derivatives, and I'm going to explain very briefly what they are. It's something that you learn in Calc 3. You don't need to worry about the details behind them, but simply put, if you've got a function that has more than one variable, you're going to use partial derivatives instead of the derivatives that you've seen in Calc 1. So, for instance, if we look at the equation for the electric field, it has two variables, x and time. And so if we want to take the derivative with respect to x, what a partial derivative is telling us is that treat time like a constant. So everything else other than the derivative in question, then the variable in question is a constant, is treated like a constant. So if I wanted to take the partial derivative of e with respect to x, it would end up giving me negative e sub 0 sine kx minus omega t times k, which is the constant in front of x. So notice that we treat t as a constant here. So let's do that. So dE dx gives us negative e sub 0 k sine kx minus omega t. And let's do the same thing for each of these. So if we take a look at the two equations up top, we're going to want negative dB dt, then we're going to want dB dx, and we're going to want negative mu sub 0 epsilon sub 0 dE dt. And then we're going to set these things equal to each other to come up with our final equation. Okay, so negative dB dt, we've got a negative sign to begin with, and then we've got a negative sign because of the cosine term, and we have another negative due to the negative omega that we're that's our coefficient. So if we have three negatives, we're going to be left with one negative. And so negative dB dt equals negative b sub 0 omega sine kx. dB dx is the partial derivative with respect to x. So we treat everything else as a constant, and we look at the b equation, and we can see that this is the result we get. And finally, negative mu sub 0 epsilon sub 0 dE dt gives us this equation. So notice each one of these four has a sine kx minus omega t in it. So we can see automatically that when we do our equations, they're going to cancel. So here is the top equation plugging in for what dE dx and negative dB dt equal. And once we cancel our sine equations, sine kx minus omega t from each side, And of course, if we cancel the negative signs, this is the equation that we get. So it's pretty simple when all is said and done. So let's do the same thing with the bottom equation, dB dx. So dB dx gives us these two sides. And when we cancel the negative signs and cancel the sine kx minus omega t, we get this equation. So now we've got two equations in terms of electric field, magnetic field amplitudes, and mu sub 0, epsilon sub 0. So we're going to try and see what we can do with these. So first thing we're going to do is we're going to simplify using these previously discussed variables. So wave number, 2 pi over lambda, angular frequency, which is 2 pi f, and then speed, which is equal to omega over k, or f lambda. So we're going to need these. So here's our first equation, and if we divide through electric field divided by magnetic field amplitudes, we get omega over k, which happens to be equal to speed. So that's equation 1. From the second equation, we divide through E0 over B0, and that gives us k over mu sub 0 epsilon sub 0 omega, which we can factor and get 1 over mu sub 0 epsilon sub 0 k over omega. And we have expressions for k and omega up top, so we're going to plug those in. So plugging those in give 2 pi over lambda for k, and then 1 over 2 pi f for omega. And so the 2 pi's cancel, and we're left with 1 over mu sub 0 epsilon sub 0, 1 over lambda f. But it turns out that lambda f is speed. So this is saying that electric field over magnetic field ratio is 1 over mu sub 0 epsilon sub 0 times 1 over nu. But from equation 1, we have that nu is equal to E sub 0 over B sub 0. So that means that we have an equation in terms of only speed, mu sub 0, and epsilon sub 0. And that's the equation we want because it's a simple equation that shows the square of the speed of this wave is equal to 1 over mu sub 0 epsilon sub 0. Wow. And these are constants that we know. And so this is saying that all electromagnetic waves travel in a vacuum at the same speed. And that speed is a fixed constant. So if you can't guess what that speed is, you can calculate it. So we're going to name the speed of light, and it uses the variable c, and the relationship is that speed is equal to 1 over mu sub 0 epsilon sub 0 in a vacuum, and speed is equal to lambda f, which means that every electromagnetic wave has a single wavelength associated with a single frequency, so you can't have multiple wavelengths and the same frequency. So we can calculate, and that's what this is showing, the speed of light to be 3 times 10 to the 8, roughly, meters per second. So please take time to verify these units and to go through this calculation. So now we need to look at energy transported by electromagnetic waves. And as we said before, these waves consist of a magnetic field and an electric field, each in phase with each other, each carrying a certain amount of energy. So we can add those two energies together. Notice, if you were to take a step back to the previous slide, we have a relationship between electric field amplitude E sub 0 and B sub 0. And it turns out that that ratio holds for all points in the wave. So we can divide through electric field by magnetic field strength at any point, and they will still equal 1 over epsilon sub 0 mu sub 0 square rooted. So that's where this equation comes from. B squared equal mu sub 0 epsilon sub 0 E squared. So this is the relationship between electric field and magnetic field strengths. Now if we plug in for B squared, we see that the total energy in this electromagnetic wave is equal to 2 times the energy in the electric field. And if we could also juggle this equation around to show that it's 2 times the energy in the magnetic field. So what this is saying is that equal amounts of energy are carried in the magnetic field and in the electric field. So we can ask questions like, how much energy will pass through a given area at a distance from, say, a radio tower? So if we're 5 miles from a radio station tower, how much energy can we expect to pass through our house and to be collected by, say, a satellite dish that we're picking up that signal from? So we know the cross-section of that dish, and what we can do is determine what the volume of energy captured is in a given unit of time. So how would we do that? It's cross-sectional area times thickness. And the thickness in that amount of time would be equal to speed dt, which gives us units of meters, which gives us the units required for our thickness. So speed times small change in time dt multiplied by area gives us small volume dV. And if we multiply our energy density times that volume, we're going to get small amount of energy passing through that area, du, in a given amount of time. If we divide that du by area and by dt, we're left with the energy per unit time per unit area, which is really what we're interested in. Because this is going to tell us how to design the cell phone or radio or television tower so that it's transmitting enough energy or enough power to travel a given distance. So this capital S variable gives us the energy per unit time per unit area in terms of electric field. Now we can also represent this in terms of magnetic field because we have the equation that says E over B is equal to the speed of light. So we're going to do that next slide. Okay, so we split out one of the E's in the E squared term as speed of light times B. So now what we have is energy represented as E times B. So recall before we said that we can determine the direction as E cross B. Now we can determine the direction of energy transported. And this is called the pointing vector, and it's basically saying that E cross B gives us the magnitude and the direction for energy per unit time per unit area for this wave. So I know this was a lot of material. Hopefully most of it makes sense, and we'll get practice in class. Okay, so one other quick note before I wrap this up is that light is an electromagnetic wave, as I mentioned. Hence the rainbow-colored spectrum that I'm showing on each of my slides. And this chart here shows the wavelengths and frequencies associated with a number of different electromagnetic waves, including radio waves, microwaves, infrared, ultraviolet, etc. So you'll probably use some of this stuff in homeworks as far as calculating wavelength if you're given frequency, etc.